Good morning, everyone. Hi, thank you for being here on time. I'm impressed. 9 o'clock in the morning. So, what are we going to talk about today? Today, I'll be speaking about SQL-on-FHIR. My name is Alexander Sicular. Everybody calls me Sasha. For those of you who are Russian, you'll probably know why. And I work at Google, specifically in the healthcare and life sciences vertical of Google Cloud. So a little bit about me. I'm currently at Google working as a solutions consultant, where I run around to many different places, many different folks, speak to folks around how to do healthcare in the cloud. How do you get from where you are today to where you want to be in the future? It's obviously challenging. That's why we're all here to discuss it. My background, though, is specifically in medical informatics. I was a director of medical informatics at Columbia for quite a while, and that's how I got this interesting background in healthcare and in technology, really interested in databases over the years, built a lot of systems in this space, particularly at Columbia and other areas, on how to write software in a healthcare environment for many different use cases. Principal data acquisition, secondary use, etc. So before we get started, I just want to make sure that we're on the record here. Everything I say is on me. Anything I say about any Google products is not definitive or authoritative. Things that we won't get into in specific detail in this session, any details around GCP in particular, Google Cloud Platform, our healthcare API, Bigquery. I'll try to kind of skirt through some of the particulars there, or how to create, for all of my American friends, HIPAA-related or aligned projects in GCP. You know, tools can be dangerous, so use them wisely. What are we going to talk about today? I want to cover the agenda from top to bottom, and then we'll kind of get into it. So, SQL-on-FHIR. Why do we even want to do it? What is the need for it? Why would people even consider putting their FHIR data into a relational-ish type of database so that they can access it over SQL? What's wrong with you? Why would you ever want to do this? We'll get into some of that. For those of you who've worked in the space, where in the story do we pick up this journey? So I'll speak about that a little bit. I'll definitely surface the SQL-on-FHIR spec that came out a couple of years ago. It's kind of the impetus or the general industry understanding of how one might do something like this and what would that best practice look like if you were going to try and attempt it. Why is this so difficult to work with in the relational world? Specifically, we're going to talk about some of the nested data types, in particular arrays and structs. How do we fix that problem? Of course, SQL gives us a solution there as well, unnest, and we'll talk about that as well. What we will talk about is what this data actually looks like once you get it into a relational space. And I'll talk about how we do it at Google and what are some of the opportunities there. For those of you who are staying for the next session, the hands-on, there's a lab. You'll get to walk through the lab and kind of get your hands dirty and play with some of the stuff yourself. I'll walk through particularly where would everybody start when they would start doing something like this. They would start at, or at least I would start at, the patient resource. How do you play with the patient resource? What are some of the opportunities there? Why does it work exactly the way that it works? We'll review what that resource looks like in FHIR and then what it looks like in SQL. And then how do we move forward from here? What can we take away from this conversation and apply in your own environments if you were to try and attempt to do some of these things in your own environment, what would that look like? Okay, so why SQL-on-FHIR? So the FHIR server that we all know and love, in my mind, it's principally useful for principal data acquisition. So day-to-day operations, transactional operations, operations in the field real-time or pseudo-real-time, operating over one or a handful of resources at a time to service a real-time use case. So think principal data acquisition where you have an EHR, patients are being seen in an environment. Of course, this is simplistic, but patients are being seen in a specific environment. You're at the bedside with the patient, you're collecting information from the patient, it's going into the EHR. The EHR is potentially sending that data or storing that data as FHIR specifically. So for me, the FHIR server represents operations in that space. Then there's an entire world that lives outside of principal data acquisition. This is a world that often in academic medicine is referred to as secondary use. So what does that mean in particular? It's everything else, everything that the EHR is not meant to do natively. Retrospective and prospective analytics. This is obviously a big space for anybody who's in research or in operations or in quality. Obviously artificial intelligence, machine learning. So these are, again, secondary use applications. All of these applications in the analytics space want to collect as much data as possible. They want to do it using tools that are part of their tool chain, part of their ecosystem. How about business analysts who want to execute over data from within their business analyst tool sets, like Tableau, let's say, for example. Finally, some of my personal interest in this space is around the area of data exploration. So discovery. These organizations have amassed vast quantities of data, and clearly there's an interest in getting access to that data. How do you expose that data for exploration purposes? How do you determine what it is that you want to do research on if you don't know what you have? And oftentimes, folks in this space refer to this as, cohort selection, cohort building, things of that nature. So you take your entire corpus of data, and then you find a way to narrow it down, get sub-cohorts. Finally, a very interesting space is, of course, cross-modality analytics. So what does that mean? We're obviously talking about data coming from the EHR, persisted in the FHIR format, so this is generally clinical informatics. But of course, as we all know, there's more to the story. I think there's a session at some point, perhaps later today, on DICOM and FHIR. So imaging, where does all that imaging data reside? All of that sweet DICOM data, with all that really rich and interesting DICOM metadata that wants to naturally get connected to all the other clinical data. Let's also throw into the mix omics, genomics data. Where are all the variants? Show me your VCF files. How do I connect those into the rest of my data sets? How about perhaps non-directly clinical related items like social determinants of health or financial information, financial data? So these are data sets that exist outside of the world of FHIR. Some yes, some no, but There are plenty of data sets that exist outside of the world of FHIR, and how do you connect them with FHIR data? Historically, the place to do all that connection is in a relational database of some flavor. So for today's journey, I'm going to throw up this hypothetical kind of pipeline of where data comes from, what happens to it, and where are we in this story today. So you have lots of different kinds of sources of data, from HL7v2, XML, our favorite CSV, and if you're lucky enough, you have source data in actual FHIR. But it's been my experience when, out in the world, working with organizations in this area, there's plenty of data in legacy formats. So then you're going to transform some of those legacy formats into FHIR. That's a lot of magic. I'm not even going to get into that. Lots of magic in the transformation. Ultimately, you get FHIR out the other end. Where do you put this FHIR? It goes somewhere. It's files in a disk. It's in a FHIR server. It's in Google's FHIR API. It's somewhere. Then the question is, how do you get this data into a relational database? Yet more mapping and transformation magic. Thankfully, Google provides some tooling that allows you to kind of skip some of that tedium and automatically gets your data from its FHIR store to its Bigquery database, and you don't really have to do anything about it. It just happens, and I'm very, very happy for that. And so today, we are hopping in right at the database. So we've skipped all the hard stuff, and it's all easy from here on out. The data is already in the database, and that's where we're going to pick it up. So I think it's really important that we kind of collectively have an understanding of where some of this stuff came from. A guy by the name of Ryan Bush, I'm sure he's well known in this community here, put together a SQL-on-FHIR kind of manifesto. It's actually a very interesting read, pretty quick read, go through it, and here are a couple of things that I pulled out of it. So you basically want to materialize the FHIR in a relational database, a quote-unquote a projection. So think the patient resource. If you were to take that patient resource, what would it look like if you were going to put it into a relational database? And Ryan goes on at some length to talk about what that might look like. And in fact, it was this document that helped kind of point some Google engineers in the direction on how to do this. And if we were going to do something like this, what would it look like? What would those data type conversions be? What would some of those native elements that would get persisted in the relational database, what would that look like? So in this document, Ryan goes to point out that some of the reasons that one would want to do this is specifically to enable analytics, and particularly a couple of different tools, including things like R. Interestingly, he does pick up on one particular advantage of relational databases versus, let's say, document store systems. Relational databases can be, they come in two major flavors, row-oriented or columnar-oriented. And so by putting this document, a resource, into a relational database, one could put it into a columnar-oriented database, and in so doing, basically reap all the rewards of using a columnar-oriented database. You know, one of the knocks on FHIR is that these documents are very, very large. And so when you want to retrieve some of this information, you know, the database has to go onto disk and it has to read all the stuff off the disk, and It has to pick out the specific things that you want. In a columnar-oriented database, you tell the database which items you want, and it only gets those items. It doesn't get anything else. So it's hyper-efficient from that perspective. And efficiency is obviously what you want to drive towards when you are building these systems that could be operating over tens of thousands, hundreds of thousands, millions, plus, total number of resources. So why is this a particular concern? For those of you who work in the relational database space, you know that we like our rows very uniform. And as soon as you start nesting and putting things like arrays and structs into these databases, it becomes very difficult to reason about how you're going to retrieve that data through SQL. And incidentally, that's what we're here to talk about today. So what I'll be using to demonstrate some of these items today is Bigquery. And I did say that I wasn't really going to go into much details here, but Bigquery is in fact a columnar-oriented database. And it has many advantages in this space. But what I think one of the most interesting things about Bigquery is that it speaks standard ANSI SQL. So for folks who have relational database expertise, adherence to standards, right? We're all here at a standards conference about FHIR, but adherence to standards in another space like SQL is advantageous. And I think I'd be preaching to the choir, talking about how adherence to standards is a good thing. So if you're looking at this and you know FHIR, then you can recognize how some of these native FHIR elements need to be stored in a relational database. There are arrays, there are complex types. There's complex types of arrays, there's arrays of complex types, and back and forth. And now it starts to become clearer what data types in a relational system you would need to take advantage of to be able to store these FHIR resources as close to natively as possible in the relational environment. Now the problem with this, as I kind of briefly touched on, is how to get the data out. Once you put it in, if you've leveraged these types like arrays and structs, it becomes very difficult to get this data back out of the system because once the data is stored as an array or struct, these kind of nested elements, repeatable elements, you can't directly access them through the common select statement. So the way out of this problem is the standard SQL library function unnest. And unnest will basically hoist whatever is repeated in these nested elements to kind of top-level structures in the SQL environment. So unnest can be used for both arrays and for structs, and you can, in fact, continuously nest unnest statements to get at whatever you need to get at. And it, in fact, is the way that we kind of are able to undo this problem that we found ourselves in. So what I want to do is talk about what that would look like. So as soon as you get data into this database, you need to be familiar and facile with what that data looks like in the database in particular. And the way that you would do that for Bigquery is by interrogating information schema. And this concept is not unique to Bigquery. It's available in almost every relational database, how to interrogate the database itself so that the database tells you what its schema is. And in Bigquery's case, there are two particular, they're actually called views in the Bigquery world that gives you information here. So the first one is columns, and it will give you only information on all the columns in a particular table. And by the way, tables, there's a one-to-one correlation between tables and FHIR resources. So for example, the patient resource will get a patient table in the Bigquery environment. And so being able to interrogate that information, and as we'll see later, programmatically is obviously advantageous. Two particular kinds here, columns and column field paths. Column field paths is particularly interesting because it will then look into these nested elements and pull some of that information out so you can then have it at your disposal to iterate over, do whatever you need to do programmatically. So this is what one of these queries looks like. And I'm just going to take a moment. Let's see if this will actually work. We're going to pull it up in the environment and execute some of these queries pre-existing database. And I'll kind of iterate through a few of them just so that everybody in the audience can see what this actually looks like in the environment. So what I'm doing here is I'm actually getting everything from the information schema columns view of the FHIR 20K patients lossless schema. So what's interesting here is, you probably can't make it out, but at the bottom you see 167 rows. And we're just going to page through it. So this will look familiar to those of you who have, intimate understanding of the various FHIR resources. Here's, for example, allergies, care plan, etc. You can see them all here. You can see all of so those are the tables. You can see in the column names, the various top-level column names of those resources. And then the next column over is the ordinal position, so where it actually falls in the order of the columns. And then you get a little bit more information, particularly around the structs and the arrays for each of those individual items. So I had mentioned that Healthcare API, FHIR API service can export data into Bigquery, and it can do it in two different fashions. Basically two different schemas. One is lossless, which we're seeing here, and the other is analytics. So let's open that up very quickly and see what that looks like. So we'll just comment out this line, and we'll get the same thing for the analytics format. And one of the interesting things right away that you can see here is, whereas in the lossless environment, you had about 160 some odd columns, in the analytics environment, you have about 400 columns. So what Google is doing in this case, when they're exporting via the analytics schema, is they are flattening some of those structs. Not necessarily the nested records, the arrays, the repeatable elements, but particularly the structs. And so when you flatten that out, what you end up with is more columns. And you can see that played out here. Let's take a look at some of the others. And this is running right now against a synthetically generated set of about 20,000 patients from Cynthia. Cynthia is like your best friend when you're playing with this stuff. So you can see how I've switched over to the column field paths view, and now I've returned a different insight into the schema in this particular version. So again, one for lossless And then finally, we'll pull up the other one for analytics, just to have a complete view. So whereas the lossless version of this shows about 1,000, 1,100 or so elements, the analytics version of this shows far more than that, about 11,000. And this kind of tells you the flattening that's taking place, again, on your behalf. It's obviously opinionated. And what's interesting about it is it puts the consumer, it gives the consumer the opportunity to determine where they want to be, which schema they want to use, one or the other or both, depending on their use cases. Okay. So let's hop back in here. Let's talk about the patient resource in particular and use that as the model going forward because they're all fairly similar. So the pattern represented in the patient resource in particular. So these are some screenshots taken from the FHIR documentation site. I think it's specifically for STU3. What we see in the patient resource is that the identifier is repeatable, specifically the identifier element within the patient resource, and this is where everybody puts in all of the numbers that everybody really wants to know. Nobody actually wants to know the FHIR server generated ID of the specific resource because it doesn't correlate with anything. The numbers that actually matter are things like the medical record number. That's what actually matters because that's what correlates with all the other data sets in your environment. So if we drill further into the identifier, we'll see that the identifier has identifier type. The identifier type is a complex type, according to the FHIR definitions. And so when we look at it in JSON, this is what we can see. So the identifier is an array. The identifier type turns into an object. Identifier type coding is an array of objects. And so now you can connect this back to the specific data types that are available in various relational databases, particularly the array and the struct. So this is kind of where the rubber meets the road. And again, for those of you who are staying for the next session, you'll be able to kind of get a chance to actually execute this query on your own. But again, I'll page out to Bigquery, and we'll get a chance to look at this query specifically. And we can step through and talk about what this query is doing. So obviously all I'm getting here is the resource ID specifically and the identifier.value, and I'm aliasing that as the MRN. So how did I actually get it? So first of all, we got to get into the actual patient resource table. And just reading from the top to bottom, we have the select statement, then we have the from statement. Then the first item there is specifically the location of this particular table. And then this is an example of how we use unnest. So recall, each of these items are repeatable elements, basically arrays. That's how they're stored as a data type in Bigquery specifically. And so if you want to actually access them, either from the select statement or from the where clause, you basically have to unnest them. So you think about it as like unwrapping a table within a row. And in this case, twice. Because that just happens to be how the FHIR resource is structured. So if if you were to do your investigation, and please take time in the hands-on if you're staying, the identifier element, as I had mentioned, is an array, so it's a repeatable element, so it needs to be unnested. And we do that here with these commands. We're unnesting specifically the identifier. We're aliasing it as I. And then we go a step further. We unnest identifier.type.coding specifically to get to the identifier codes. And this is where you would see things like driver's license, social security number, PPN is passport, and of course MR for MRN. So if you specifically only want to get to MR codes, like just MRN codes, you have to dial it in. You have to put it in the where clause. So you have to say, in this case here, how I did it, it.code equals MR. And this is how you're assured that you're only accessing MRN codes versus any of the other identifiers that may be there. And here in particular, before I go there, I want to talk about like how this gets joined, because this is a very important thing as well. For those of you who've worked in the space, in the relational space, obviously there are many different types of joins. Left joins, right joins, and all the joins in between. This particular join is specifically a cross join, but in particular it's a correlated cross join, which means that the database is smart enough to know that the elements within that particular row are specific to that row. And for those of you, why that matters is because for those of you who've done this before, cross joins are generally a problem. You end up getting a Cartesian product. Basically, the rows that you return is the product of the inputs on both ends when you do the cross join. But in this particular case, the query engine is clever enough to know that these items are within a specific row in the database layout. And so if you notice, you don't specifically have to join them to the other table. So that's a particular thing to keep in mind. So again, moving forward, we're talking about the MR. We obviously just want to get all the items of the MR, and then this is how you would specifically push in an MRN. Just uncommented there. This actually is valid. I tried it before. That's how I got the number. Yeah, and there it is. And that's how you would just get one or more. You could put in an in statement, or in fact, this is how you would join that value into other resources down the road. Okay. For those of you in this space, you may have heard of the ECQM, Electronic Clinical Quality Metrics, which is a whole bunch of metrics, or basically queries over clinical data. Tell me things. And there's an organization that puts them together. Feel free to take a look at them on your own time. But I do want to show like what a complicated query looks like, specifically to solve one of these EQM metrics. And we're going to look at diabetes. One of the fun things about Bigquery is it lets you keep all your queries, and then we'll just pull it up. And we'll step through this query. It's involved, but it's an example of how you would need to manage the complexity of the data in the system. And I'm going to go through it rather quickly because I think I have a few minutes left. So this particular query is diabetes. Basically, find me all my diabetics, and then find me the diabetics that have an elevated A1C reading. So how would you actually construct this? So I'll step through this query and point out some of the particulars here. So the with statement at the top here, this is a CTE, a common table expression, and it's often used for opportunity to create legible queries. So you separate some of your subqueries into their own different components, and then you can use them later down the road. So the first component here is my maximum observations. Find me everybody with diabetes. The particular thing to note here are these items. So safe offset. Recall I was talking about how these queries in the system are flattened from the struct perspective, but not from the repeatable nested perspective. So a repeatable nested is an array, and in order to access the array, you need to unpack it, basically. So safe offset 0 is the first element of the array. Bring me that. And so you see I use it, throughout. Row number, partition by, it's a way to get the top element. So I only want to get the reading from their most recent reading. Doesn't matter if they've had this valuation sometime in the past. I want the most recent one. So this is how I'm able to do that, get the row number. Then I want the population. Give me the full, so the max observations is the one for folks who have a high reading. Then I want the full population. This is this CTE here, where I'm simply getting people by age. One thing that I want to note here is I'm doing a date diff to get the age, and in this case it's 18 to 75, so between 18 and 75. But I'm doing it with current date. So current date gets evaluated every time you run the query. So what that means is current date will change as you run the query at different times. So you run the query into the future. So this is something to consider if you have to have it dynamically evaluated at query runtime or statically input into the query so that it's repeatable, so that you're always querying the same date range. And then finally, there's some tricks that are happening here to get to ultimately this, which is what the ECQM wants, which is basically a ratio. It wants to know like how many of your diabetics have elevated readings. So I think I'm going to get the hook soon, but we more or less got to the end of this presentation. I'm kind of surprised. So the way forward, repeatability. If you were going to try that and do this in your environment, I would highly recommend that you don't write SQL code. Rather, you write code that generates SQL code. Because this is not the kind of SQL code that you want to write by hand. It's non-deterministic. So when somebody comes to you and asks you a question, it might get routed to one SQL developer of a certain skill and a certain knowledge of your environment, or it might get routed to another one. And ultimately, they'll write SQL that's not identical, in which case you have this determinism issue to deal with. I would definitely take a page out of what's happening at Odyssey Atlas. Think about, obviously it's a cohort building generating environment. How can we get something like that for the FHIR world? Then I would look at views, intermediary views. So the work that he did on the patient to create that, very basic table with just the reference ID and the MRN, maybe that's expressed in a view in your total environment so that any other queries that need to access it can just access that and not have to write all the SQL for it. Finally, I'm done. I actually made it to the end. Thank you for bearing with me. I have 1 minute left for questions. Yes, sir.
I suppose you also did some code generation, SQL generation on the structure definitions?
Yeah. So I have dabbled in some of that myself to do code generation specifically for patient longitudinal record. Basically get me everything for either all patients, a group of patients, or a specific patient. And that query is unfortunately terrible. So it's the kind of thing that you don't want to have to write by hand because you'll miss things and you won't be deterministic. And that's actually what you want to do. It's not trivial to do this kind of thing, to write code that generates SQL. But I think for folks who are looking to productize this in an actual environment, I might suggest that it's one of the only real ways to go about doing it.
Are there open source projects that already do that?
If there are, I'm not particularly certain what they might be. They may be. If they are, I'd love to see them. If you know of any of them, please tell me. Thank you. Any other questions? Otherwise, you'll get an opportunity to play with all this stuff if you hang around for the hands-on. Thank you.